Welcome to the video presentation for the assessment of Henkin burner platform for measurements of unstretched flame speeds. My name is Matthew Brown, presenting a summary of the work done by myself and fellow graduate student Marcus Brown under the advisement of Dr. Erica Belmont. Due to the significance of laminar flame speeds in combustion, great effort has gone into accurately measuring the flame speeds of various reactant mixtures. However, flame speeds can be affected by aerodynamic stretching of the flame front caused by the geometry of the measurement platform. The Henkin burner has been proposed and used in recent years to measure propagation speeds. This study expands on the work performed by Umbrella and further assesses the strain rate of laminar premix flames using the Henkin burner and compares the results of two flame speed measurement techniques. For this study, a methane air flame was stabilized using an experimental chamber that was held at 16.7 kilopascals. Once the flame was stabilized, particle image velocimetry was performed to measure the axial flow field. The axial flow field was then used to determine the axial velocity profile over the center of the burner surface. This profile was then used to determine the minimum axial velocity and upstream axial velocity gradient just upstream of the flame front. The minimum axial velocity is the stretch flame speed, while the upstream axial velocity gradient represents the axial strain rate of the flame. This process was repeated over a range of volumetric flow rates, and the corresponding stretch flame speeds were plotted as a function of axial strain rate. Once again, this process was repeated for both fuel lean and fuel-rich cases. Using these measured properties, an unstretched flame speed can be approximated by extrapolating to zero axial strain rate. The first and simplest approximation uses a linear extrapolation and finds flame speeds ranging in value from 45 centimeters per second to 58 centimeters per second. Next, a nonlinear extrapolation developed by Etienne and Matalon results in similar unstretched flame speeds. Differences were found to be at most around 4%. Next, a less generous flame speed measurement technique was examined. Chemiluminescence imaging can be used to precisely pinpoint the flame location above the burner surface. This liftoff height is measured for the same flame over a range of reactant flow rates. By plotting the liftoff heights as a function of flow rate, two regimes become apparent. The intersection of these regimes can be used in conjunction with known operating conditions to calculate the flame speed. Now, if we plot the unstretched flame speeds predicted using the PIV technique and we overlay the calculated flame speeds using the chemiluminescence technique, we can see that the chemiluminescence technique predicts very similar flame speeds. In conclusion, one-dimensional adiabatic flames were stabilized using a flat flame Henkin burner platform. PIV results showed that flames experience very little axial strain. Consequently, the linear and nonlinear extrapolation methods produce similar unstretched flame speeds. Additionally, the chemiluminescence measurement technique produced flame speeds nearly identical to those determined using PIV, which further supports its use due to its accuracy and relative simplicity when measurements are performed using a flat flame Henkin burner at subatmospheric conditions. With that said, thank you very much, and are there any questions?